Our last couple shapes that we're learning the properties of today are kites and trapezoids. So on the last set of notes, I said that one of the shapes that we just labeled as a quadrilateral in general, having 4 sides, it's actually going to be called a kite. So let's look at the kites. Now these are not parallelograms, so none of the parallelogram rules apply for a kite, but it straight up looks like a kite that you would go outside and fly. The rules for a kite are that it has 2 pairs of consecutive congruent sides. Let me make that a little bit clearer because that looks like 3 squiggle lines. Congruent sides. So that means this time, unlike a parallelogram, the congruent sides are not going to be across the figure, they're going to be touching each other. So in our image here, to show our consecutive congruent sides, I want you to put 1 tick mark on AB and 1 tick mark on AC. Those are consecutive sides, meaning they touch each other. Those are going to be the ones that are congruent. And then we're going to have 2 tick marks on BD and 2 tick marks on CD. Those are consecutive sides. So those are congruent. Notice that opposite sides here, what we're looking for in a parallelogram, opposite sides are not congruent in a kite. So looking across the figure, these are not congruent sides. That was a property of parallelograms. The second property for kites is that we have perpendicular diagonals. Now that is a property that rhombi had, but we know that the perpendicular diagonals are all going to make 90-degree angles. So we can put a nice, cute 90-degree angle symbol where all of those diagonals meet. The third property is that we have 1 pair of opposite angles that are congruent. The pair of opposite angles that are congruent are like on the wings of the kite. So angle B, big angle B, and angle C, big angle C like this, those are congruent on the wings of the kite. The other 2 angles, A and D, those are not congruent. We only have 1 pair of opposite angles that are congruent. Now there is a fourth, it's called a corollary. It's not a property necessarily, but we're going to think of it as a property for this shape because it follows and it's something that you need to know. So we're going to label it number 4, but it's not technically a property. It just follows from the property. And that is that the major diagonal bisects the minor diagonal. Let's figure out what that means. Number 1, bisects means to cut in half. What do we think I mean by major diagonal and minor diagonal? What does major versus minor sound like? Like something's the majors versus the minors. What do we know about those words? Big and small. So you can think of this as the big diagonal bisects the small diagonal, which means the small diagonal we can put 3 tick marks on because the small diagonal will be perfectly bisected in half, but the long diagonal, not so much. And visually that makes sense because pretty obviously this chunk is not the same as this chunk. So those are not going to be bisected, but the minor diagonal will be bisected, or the smaller diagonal. So those are the properties that we apply to kites. It will allow us to answer lots of questions, kind of like we did for parallelograms and for the squares, rhombus, and rectangles. So obviously I've done the work on these because at this point in this class you know how to solve for x, but I want to show you how to set this up. And the property we used in this problem is the property that the kite has opposite congruent angles. Take a green highlighter and I want you to highlight this x and this x. Those angles are congruent, meaning they are the same number. So if I'm looking for the angle K and the angle L, I can put those as a missing variable x in my equation and I can solve for x. Here's what I did in this problem. I threw it back to information we had on day 1 of this unit, and I said, if this object has 4 sides, then its total interior angle sum should be 360. I got this from the purple formula chart in the center of your table. So then I said, okay, let's take all of the angles from inside that shape, x, 90, another x, and 130. I'm just taking the 4 interior angles, and I'm adding them all up, and I'm setting them equal to what number? 360, because a 4-sided figure has 360 degrees on the inside. And then it's just quickly solving for x. I got that x was 70, so that means that this angle and this angle are both 70 degrees. So we use the properties of kites to apply it to an algebraic problem. In question number 2, let's highlight the important things here. It says find the value of x, y, and z. We're actually going to start with y and z because they're way easier. I noticed that y is right here. It's the side length GF. But based on the fact that these have 2 pairs of consecutive congruent sides, if GH is 4, how much is GF? 4. That's why y is 4. Same idea if if FE is marked with 2 tick marks and is 13, I'll make two tick marks with my highlighter. What is the value of Z? Also 13. So those 2 questions, really simple. If you have one of the side lengths, then the consecutive side length is the same. But when we solve for x, we're using that extra property that we wrote down. Because if you notice, 9 is on one of the minor diagonal pieces, and 1/10 times x equal or minus 1 is on the other minor diagonal. But the things I know about this is that this part and this part are congruent. Mathematically, congruent means equal. So what I did is I set up this equation right here where I said the top part of that minor diagonal has to be congruent or equal to the bottom part of that diagonal. After that, I just solved for x. In one of these problems, obviously, I used the box method to do this, and in the other, I used inverse operations, so you can see both ways. They both work. Choose whatever you like. And yes, you'll be dividing by 1/10. That's okay. Use your calculator, and you can do it. Sound good? That is all that you need to know about kites. You know about their consecutive sides, the 1 pair of opposite angles that are the same, and the minor diagonal. Okay, then we move on to trapezoids. Does this shape look somewhat familiar to you, a trapezoid? Okay, we're going to talk about a regular trapezoid and then specifically an isosceles trapezoid. But just before we get started, I need you to know how I'm talking about this shape. So when I'm talking about the base is of a trapezoid, I'm talking about the legs that are flat. The sides that are flat. Base 1, base 2. Doesn't matter which one's 1 and 2. For most trapezoids, you can call it the top and bottom, but they might be turned sideways, so don't call it top and bottom. Think of it as a base. They're the ones that are parallel. Your legs are the ones that are in between, the ones that are tilted. That's a leg. So in a trapezoid has exactly 1 pair of opposite sides that are parallel, and specifically those bases are going to be what are parallel. They go the same direction. That's why they end up looking flat. Guys, can we pay attention for a sec? The other property for a regular trapezoid is that you have 2 pairs of angles on the same leg that are supplementary. And remember, supplementary means that they equal 180 degrees. So it says 2 pairs of angles on the same leg that are supplementary. So we have to make sure we're looking at the leg and saying that this angle on the leg and this angle on the leg will be equal to 180 degrees. Same thing on the other leg. This side of the leg and this side of the leg will be equal to 180 degrees. This does not fit for the sides of the base. They have to be the angles on the legs, not the angles on the base. Okay, that's a general trapezoid, and those are the only properties of a general trapezoid. But probably the trapezoid you think of when you think of a trapezoid is the one that kind of looks like the Pizza Hut. That is technically an isosceles trapezoid. Since we've added the word isosceles, we've added a few properties, specifically that the legs are congruent, meaning that those sideways pieces are the same size. We couldn't assume that in the regular trapezoid, but if it's an isosceles trapezoid, we can assume that. Since those legs are the same length, that then means that each pair of base angles are congruent, meaning angle A and angle D are the same length, the base angles, and angle B and angle C are the same, the other base angles. So both the top angles and the bottom angles, if it's a flat trapezoid, are the same. And then last but not least, the property that we have here are that the diagonals are congruent, which just means this entire diagonal here is the same exact length as this diagonal here. So both the pieces are the same. Again, that's a lot of properties floating around, so we need to make sure we're using these notes to keep track of what properties go with what shape. That's going to be extra important because we've now learned 6, 7 shapes. We got to keep them all straight. For number 3, we've got to work this one out. It says to find the missing values. It wants me to find K and find M. Now, this is not an isosceles trapezoid. Why is this not an isosceles trapezoid? In an isosceles trapezoid, look at property 1. What must be congruent? Is this one marked where the legs are congruent? No, so we know this is just a regular trapezoid. But what we know about regular trapezoids is that the leg angles have to equal 180 degrees. They're supplementary. So we can do 2 tiny little math problems and we can say, all right, well for M, what is 180 minus 87? Because they need to add to 180, so if I take away 87, I can just find out that letter M is equal to 93 degrees. What's the tiny little math problem I'll do to find K? I agree. For the other side, 180 minus 51, which fast forward through that math, is 129. So we can use the idea of supplementary angles to find the missing angles in a trapezoid. Now I've pointed this out to you already for number 4, but I've said to you this is an isosceles trapezoid. How do I know this is an isosceles trapezoid? What is now marked on there that was not marked on the last trapezoid? The legs. It has the markings to tell me that the legs are the same length. So we know this is an isosceles trapezoid, so we can now use the properties 1, 2, and 3 right above this. If we're finding angle L, that means I'm looking for this angle right here. Well, that is a base angle. And number 2 property up here says the base angles are congruent. So if this base angle on the long base is 23, what's this one? 23. So that means angle L is 23 degrees. The other one I want is angle K. So let's highlight angle K for ourselves right here. We don't know angle J, so it's not as easy as the question before this where we just said 23. But since we know, and I'm going to zoom in because I need to write a little bit smaller. If we know this is 23 degrees, what do these two angles have to add up to? 180. So what is the tiny little math problem we'll do to find K? 180 minus 23. And if we do 180 minus 23, we're going to get 157. I know you trust me on that math. So the angle K is 157. Bonus question that's not written here. What is angle J? 157, because these two angles have to be the same measurement. Very good. Okay, those ones have no algebra really in them, just some arithmetic. To show you a problem that does have some algebra in it on the back, we've got a problem that looks like number 5. It says quadrilateral ABCD is a trapezoid. So I've drawn it for you, ABCD. I marked that these are parallel, and it gave me that AD is 16x minus 13, and BC equals 9x plus 8. So I've labeled everything. Find the value of x that makes ABCD an isosceles trapezoid. The moment I see this word isosceles trapezoid, that means I know that these legs are congruent. If the legs are congruent, mathematically that means that they are equal. So I set up this equation right here where one side is congruent or equal to the other, and I'm able to solve. And then we solve for x. Again, you know how to solve for x. We're not going to go over that part. We've got one little theorem to go over. I recommend having 3 colored highlighters. It really doesn't matter the colors this time, but 3 colored highlighters for the trapezoid mid-segment theorem. A mid-segment, which we found for a triangle, is the segment in the middle of the shape. So for the triangle, the trapezoid right here, MN is my mid-segment. But there's a relationship between the mid-segment and the bases. Since it's in the middle, if you double the mid-segment, it will be equal to the length of the first base added to the second base, which gives us a formula to set up every time we do a mid-segment problem. Just like with a triangle, we're going to double the mid-segment and set it equal to something. And in this case, we're setting it equal to the 2 bases added together. Okay, keep your color scheme. However you just colored in this formula, we're going to color code questions 6 and 7 matching your color scheme so that you can look back and make sense of this formula. In number 6, it says find CD. In the image, CD is right here in the center. It is my mid-segment. I then have 2 bases, a base of 12 and a base of 36. My mid-segment theorem allows me to set up the equation that says if we double the mid-segment, it will be equal to the sum of the 2 bases. So do you see how all I did was set up 2 times the mid-segment is equal to the base plus the base. After that, you solve for x or solve for CD. This time I used inverse operations. And in the second one, I'll show you box method. But again, we are pretty good at solving equations at this point. It's just the setting up. For number 7, it says find the value of x and EH. Okay, so for this one, based on your color scheme, take the color of the mid-segment and highlight that mid-segment value. And then use your 2 base colors for the first base and the second base. The formula color scheme should look the same. So whatever color you've used for the mid-segment, it should be doubled. So I do 2 times that length, 3x minus 2, and I'm going to add the first base and the second base. In particular for this problem, before you actually start the box method, you do have to do distribution. So if you notice, I have one step before I drew my boxes, and all I did there was double 3x and double negative 2. So there is one tiny step there before you start the box method, but then you can solve using the mid-segment theorem. Now we only answered half the question here because we found the value of x, right? What else did it ask for? EH. So now that we have the value of x, what I'm going to do is I'm going to take the expression listed on EH, and what should I do with the value x? Plug it in. So everywhere there was an x, I'm going to put parentheses 9 since we found the value of x to be 9. And we're going to actually evaluate. 3 times 9 is 27. And then 27 plus 3 is what? 30. Oh my gosh, 27 plus 3, y'all.